Hello grade 11s and welcome to question number 3 on electrostatics. So this question consists of question 3.1 and 3.2, and to keep the video short I've decided to separate them. So after watching this video, please remember to watch the next one, which will be about question 3.2 on electrostatics. Now before we look at the problem, I'd like to remind you of some of the formulae that we use in this section. Firstly, we have the formula that we use to calculate the electrostatic force. This is a force just like any other forces, and it is therefore measured in newtons. We have a constant that can be found in the table of constants. This is Coulomb's constant, given as 9 times 10 to the power of 9 in magnitude. In this formula, we have the magnitude of charge 1 and the magnitude of charge 2. It is very important that you only substitute into this formula the magnitude of the charges. In the denominator, we have the distance between the centers of the two charges, or since these are tiny point charges, it is the distance between the two charges. Then on the right hand side, we have one of the formulae that we can use to calculate the electric field, or the strength of the electric field. The electric field strength is measured in newtons per coulomb. Please don't forget this. I often find that learners forget this unit. And in this case, if we are trying to find the electric field as a result of charge 1, then the force is the force that will be experienced by a test charge, that is experiencing the electric field of charge 1. This charge at the bottom is the charge on the test charge, rather than the charge that is creating the electric field. At the bottom, we have another formula that can be used to calculate the strength of the electric field. If we are interested in the electric field of charge 1, then this is charge 1's charge, or the magnitude thereof. K is a constant, and R is the distance between the charge and the point in space where we would like to measure the electric field strength. Lastly, we have a formula that was taught you in grade 10. Another way of representing this formula is to say Q is equal to NE, or you may even recognize NQE, where QE is the elementary charge. E can be found in the table of constants, and it is just the charge on an electron, given as negative 1,6 times 10 to the negative 19 coulomb. N is the number of electrons, and Q is charge measured in coulomb. So these are the formulae that are available to you, and you will use them together with the table of constants. We can now take a look at question 3, which says 3.1. In the diagram below, A and B are two identical spheres of unknown mass. Sphere A carries a small charge of negative 3,2 times 10 to the negative 7 coulomb, and B has a positive charge of positive 6 times 10 to the negative 8 coulomb. Sphere B is attached to a string of negligible mass. When A and B are exactly 25 millimeters apart, at this point I'd like to remind you that millimeters is not the correct unit in which we measure distance, so we need to convert this by multiplying by 10 to the negative 3 to get the value in meters, or we can divide by 1000. It does exactly the same thing. They say A and B are exactly 25 millimeters apart. When they are this distance apart, the string makes a 30-degree angle with the horizontal, and fortunately, we can see this in the diagram. Very often in these questions, instead of giving you the charge in coulombs, they may give it to you in microcoulombs, millicoulombs, nanocoulombs, or picocoulombs. To go from millicoulombs to coulomb, we're going to times by 10 to the negative 3. To go from microcoulomb to coulomb, we times by 10 to the negative 6. From nano to coulomb, we times by 10 to the negative 9. And from picocoulomb to coulomb, we times by 10 to the negative 12. Please do not forget this, and do not forget that you always substitute values into the applicable equations using the correct SI unit. Now question 3.1.1 says, give a reason why the forces acting on sphere B can be represented by a closed triangle. What do we mean when we say a closed triangle? Well, we are referring to a vector diagram, specifically a vector diagram where we have attached the force vectors or the vectors using the tail to head method. So if we end up with the closed vector diagram, we know that this implies that the net force or the resultant force on this object is going to be 0. And to answer this question, we can simply say the net force acting on sphere B is equal to 0 newtons. We write this out in a full sentence, but just to shorten it, I've only said net force equals 0 newtons, and for this you're going to obtain 1 mark. Now question 3.1.2 says, draw the triangle of forces for sphere B. Label the forces and indicate at least one angle in the triangle. So before we do this, we need to identify what forces are acting on sphere B. Firstly, we know that it is attached to a string that is attached to the ceiling. It therefore has a tension force acting on it. There's tension in the string. Sphere B has a mass, and since it has a mass, we know that acting downwards is a gravitational force called Fg. And since sphere A is next to sphere B, sphere A is negatively charged and sphere B is positively charged, we know that opposite charges attract. Therefore, sphere B will be pulled towards sphere A by an electrostatic force. That is the force of sphere A on sphere B. And these forces together can be drawn using the tail to head method to create a closed vector diagram. So you will see that this answer is labeled question 4.1.2, and that is because it has been taken from a past paper. But this is in fact the answer to question 3.1.2. So you have options. You could have drawn the diagram on the left or the diagram on the right. I'm going to go ahead and explain the diagram on the right. So first we draw in the gravitational force straight down. We remember to include an arrow. Please do not draw your arrows like this. Okay, instead we draw an arrow like this, and we make sure that we attach the arrowhead directly to the straight line. This is because when you draw arrows this way, we don't know if the arrow is pointing that way, or that way sometimes. Sometimes your diagrams are just so confusing. So please rather draw your arrows in this way. So we draw in Fg. When we're done drawing in Fg and labeling it Fg, to its head we're going to attach the tension force straight up like this, and we remember to include an arrowhead. If you do not include the arrowhead, you're not going to get your marks. We label that T or Ft or F tension. Then lastly, to the head of the tension, we're going to draw in the tail of the electrostatic force this way. There it is. You can call it F, F attraction, F electrostatic, or even Fe as I have. And as you can see, we create a closed vector diagram. Now if we go up to our sketch, you will notice that between the electrostatic force and the gravitational force, we actually have a 90-degree angle. These forces are perpendicular to each other. So we go to our diagram and we identify the electrostatic force and the gravitational force. And between those two forces, we're going to draw in a 90-degree angle. But that's not the only angle that we can include. We also see that if we move this force up over here and we move this force all the way over there, then between the tension force and the electrostatic force is a 30-degree angle. So we identify the tension force and the electrostatic force, and between the two we put in the 30-degree angle. Since a triangle the interior angles of a triangle add up to 180 degrees. We know that the last angle between the gravitational force and the tension force is actually 60 degrees, and you may include that as well. But it is very important that you include the angles in the correct place. So, for your forces drawn correctly with the arrowheads and labeled correctly, you're going to get 1 mark for each force. Then, for including one of the 3 angles, you're going to get 1 mark. I'm going to award a mark for the 30-degree angle, and this gives you a total of 4 marks for question 3.1.2. So now we can go on to question 3.1.3. And this question says, calculate the magnitude of the weight of sphere B. Remember that the weight is actually Fg, or if you'd like to, you can label it W. So when we take a look at this diagram, we have no clue what the tension force is. We also at this point don't know what the electrostatic force is, but we can definitely calculate it because we know the distance between the 2 spheres and we also know their charges. Now, unfortunately, in this diagram, it appears as though the distance between the outsides of the spheres is 25 millimeters. But we're going to have to make an assumption here. We're going to assume that these are very tiny spheres, and we're going to assume that this 25 millimeters extends to their centers. Because if we don't do that, we have no other way of calculating the radius of the spheres and therefore the distance between the centers of the 2 charges. So that is a mistake made in the question, but we're going to just make an assumption and work with it. So now we're going to answer question 3.1.3. I'm going to move this here down. To answer this question, we're going to start off by finding the electrostatic force. They don't say that we should calculate it, but in a moment you're going to see the value of calculating it. We start off by writing out the formula exactly as it is on the formula sheet. We know that K is a constant that we can find in the table, and it is given as 9 times 10 to the power of 9. So we substitute into the formula that value, 9 times 10 to the power of 9. The charge on sphere 1 and 2, we only substitute into the formula with their magnitudes. We do not, I repeat, we do not substitute in the negative values or the negatives because this formula only gives you the magnitude of the electrostatic force. If you're interested in the direction of the electrostatic force, you ask yourself, do we have forces of attraction or do we have forces of repulsion? And based on that, you will determine the direction. But this formula does not give you the direction of the electrostatic force. We take all of this and we're now going to divide by the distance between the centers of the 2 charges. And we remember that we substitute this value in the form of meters. Do not forget to square the distance. We often forget to do so. And if you plug all of this into your calculator, you should obtain a final answer of 0.2765 newtons. Do not round off this answer to 2 decimal places because this is not the final answer. All that we now have is the magnitude of the electrostatic force, which is 0.2765. Now if we look very carefully, ignoring the 60, we see that we have the magnitude of this force, or that side of the triangle, and we are looking for this side of the triangle. We also have this angle of 30 degrees. So what is the relationship between these sides and the angle, given that this is a right angle triangle? Remember that when we have right angle triangles, we can use trigonometry. Well, FG is opposite the angle, and the electrostatic force is adjacent to it. Opposite and adjacent is what we have, so we can write down what we know about tan theta. We can say tan theta is equal to opposite, where in this case the opposite side is FG, over adjacent, and in this case the adjacent side is the electrostatic force. We know that theta is 30, so we can plug in everything that we know. We say tan 30 degrees is equal to Fg divided by Fe, which we calculated as 0,2765. Multiplying up, we find out that Fg is equal to 0,159 newtons. And that is in fact the final answer to this question. We have found the magnitude of the weight of the sphere, given as Fg. Now this question is out of 5 marks, so marks will be awarded as follows. You're going to get 1 mark for what you substitute at the top of the formula for the electrostatic force, 1 mark for what you substitute at the bottom, 1 mark for your tan 30 degrees, 1 mark for what you substitute on the right hand side, and 1 mark for your final answer of 0,159. Of course, if you use this diagram on the left hand side, you might describe these two or this relationship in terms of sine 60, and that is okay. You should in that case obtain exactly the same answer, and you can find this working in your or on your memo, the memo that will be attached on the website. So, grade 11s, this brings us to the end of this problem on electrostatics. In the next video, we're going to continue with question number 3. Specifically, we're going to look at question 3.2, which involves the electric field. So please be sure to join me there.